last of these talks, so hopefully you're still ready to listen. But this one's going to be not super technical, but I have a backup slide. So if you have technical questions, ask me afterwards. Okay, so this talk is about how we remove hallucinations from LLM outputs, and it's work joint with my collaborator, Isaac Gibbs, who's now a postdoc at Berkeley, and my advisor, Emmanuel Candes at Stanford. Okay, so I figured the best way to illustrate what we're doing here is to start with an example. So it's the 60th anniversary of the Hertz Foundation, and I'm imagining that Robbie might, well, maybe she wouldn't have to, but someone in this room might have to go to ChatGPT and ask them, who is John Hertz? So if we ask ChatGPT, this is a real response, not cherry-picked at all, I swear, the first one I got from GPT 3.5 Turbo. This is the answer we got. And we don't need to read the whole thing, but those of you who don't know, ChatGPT can make things up. They're called hallucinations, and there are hallucinations in this output, multiple of them, in fact. And now the question is can we find them, can we remove them, and can we do so reliably across a variety of outputs? And the answer is going to be, for the most part, yes. Okay, but before I tell you what's wrong, I'm going to go through an initial approach to the problem. And so the first step we're going to take to even figure out how we identify what's wrong with the output is to parse it into a series of individual self-contained claims that are themselves evaluable. And curiously enough, I'm just going to use ChatGPT to do this. Because even if it can make things up some of the time, it's actually reliably good at parsing natural language. So if I do this, I'll get 27 self-contained claims. You can see them yourself. These are the real claims output by GPT 3.5. They are indeed self-contained as I claimed. Okay. Now that we have these claims, the question is which ones are bad and which ones are good? And so there's a whole cottage industry that's emerged in the AI research sector that's about finding and scoring these claims for whether or not they might be false or true. And so if you go to Google Scholar and you look up AI hallucination detection or claim scoring, there are well over 1,000 papers published in just the last 3 years in this topic. So this talk's not going to be about how we score these claims, it's what we're going to do with the scores we can compute for these claims. But just so people understand what these claim scoring methods do, one example of a way to score these claims is for me to ask ChatGPT 5 times at a higher temperature, meaning producing more random responses, the same question. Write me a short biography of John Hertz. And you'll notice that in each response there are small variations. Variations in the type of claim being made might correspond to lower internal model confidence in the certitude that it has about whether that claim is true or false. And we'll use that as maybe a score for whether or not we should keep or drop the claim from the final output. Okay, so really this talk is about how we decide when to keep a claim or to discard it. And so to understand how we're going to approach this problem, let's first start off with a pretty simple approach to it. So the approach that someone has already previously developed works in the following manner. We're going to take some other examples, some similar question-answer pairs, and we'll ask an expert to give us the ground truth annotations. For my experiment, I just used GPT-4 to actually give me the ground truth annotations. And so you can imagine if I ask for the biography of George Washington, I get these scores from whatever claim scoring function I chose to use, and then I get the expert annotations. And we do this for multiple examples. I've chosen Washington and Adams here. You'll notice there are 2 errors. And so the next thing I'll do is I'll identify the threshold for the score at which if I removed all claims whose score was below that threshold, I would have removed every false claim. Hopefully that makes sense to everyone? Okay? And then I'm going to do this for all the examples I have. So you can imagine having hundreds, if not thousands, if not tens of thousands of such examples. And we're going to compute these cutoffs that, if we knew them in advance, would give us the right threshold to remove every false claim being made in the output. And then I'm going to take the 90th percentile of these cutoffs, I'm going to pretend that it's 4.1 for this data set, and I'm going to use it going forward on new examples where I don't have the ground truth annotations. In a very strong sense, that is, if those similar question-answer pairs can be thought of as exchangeable with the pairs I'll see going forward, that filtering threshold guarantees us a 90% chance of removing all false claims. So, problem solved? Not quite. So if I run this method on this example I just saw, I remove every single claim from the output. And we shouldn't be totally surprised, because if the threshold is pretty high, then one way of guaranteeing no falsehoods is to say nothing at all. But if you're running OpenAI or Google or any of these frontier labs trying to make money selling chatbots and trying to also remove hallucinations, telling someone nothing isn't really a solution either. So what are the problems driving this issue? Well, the first is that maybe our score just isn't very good. the mechanism I showed you before for estimating the score function was pretty coarse. I just asked the model a few times to repeat itself. But also, maybe the threshold isn't really well estimated. I've learned this threshold over a bunch of examples involving presidents and basketball players. Maybe that's not so great for John Hertz. But maybe, fundamentally, 90% is just too much to ask for right now. That today, our language models aren't accurate enough or reliable enough, and our scoring functions aren't good enough to ever guarantee a 90% chance of factuality without just stripping out most of the output. So this paper, the paper that I'm presenting on, presents a method that addresses all three of these problems, and the method we're going to call level adaptive conditional calibration, and I'm going to tell you at a high level what it does, but like I said, ask me some questions. Okay, so the first thing we're going to do is we're going to estimate a locally adaptive threshold. So just to understand what this means, imagine we had groups, things like more frequent names and less frequent names. And you can imagine estimating a separate threshold for the more frequent names because we know that we can use a more or less conservative threshold to filter out false claims. You can even see this in this example I've shown you, that the threshold you need for people like George Washington and John Adams is a lot lower than the threshold you need for a basketball player or a more obscure Revolutionary War figure. But okay, this doesn't sound that complicated. It doesn't sound like I've done anything that significant because I've basically just rerun the old method on different subsets of the data set. But it turns out the method we work with also works even on overlapping groups. That is, I can define groups based off of not just the frequency, but maybe the historicity of the figure. So Thomas Pinckney is also a Revolutionary War figure, and I can still issue a separate threshold for him. In fact, I can issue separate thresholds for every single person in the group if I have a continuous covariate that I can use to sort of classify them. Okay. So once I have this, though, it's still not enough, because if I go back to the previous example, you'll see that the thresholds for Pinckney and Maxey are still far too high to preserve most claims. So what I'm also going to do is learn how to adjust the guarantee for each output in order to ensure that I preserve most of the output. So in other words, maybe there are some people where I can just never guarantee a 90% chance of factuality. There are some claims for which I just need to say that the LLM can only be correct with a 34% chance if I really want to tell you that it's 100% correct. Okay. And the last thing I want to say about this, the question of having a bad scoring function, is that we've shown how to make this entire procedure I've described, which is pretty complicated under the hood, end-to-end differentiable. And what that means from a non-technical perspective is that we can learn the scoring function through this procedure. So you can run this procedure, look at the outputs, and if you don't like something about it, you can adjust the scoring function that you're using, or learn an ensemble of scoring functions incorporating many of those methods in order to do better. So what does this method now do? So if I go back to the Hertz example, I now filter out far fewer of the claims. So I'm only filtering out that he's Hungarian-born, the particular location of his birth, the story of the start of his career, and his commitment to customer service, which, as we all know, is probably true. It turns out every claim, except for maybe the commitment to customer service, was a false claim. In fact, this filters out all but one false claim, but you might notice that 35.6% is a little bit of an unsatisfyingly low guarantee. It's less than a 50-50 chance. If I rerun this method to guarantee no more than one false claim, I actually can tell you that there's a 60% chance there's no more than one false claim in this output. And in fact, there is just one false claim remaining. That you didn't start the Hertz Drive Yourself system in 1918, it was in 1924. Okay, so hopefully I've shown you that on this example at least it does something useful, but a question that might be going through some of your heads is, well, what do these probabilities even mean? I mean, I log on to the 538 and I see that Kamala Harris is a 54% chance of winning the election. Like, what is a probability in this context? Should I really, what can I do with a 34%? And the answer is that we've shown how to calibrate these probabilities exactly. So in other words, this is the real validation set from our paper. This is on a more realistic setting, long-form medical question answering, where you ask ChatGPT for advice about your medical condition, not that you should do this. And we show that the probabilities we issue are calibrated, meaning that if we claim that you have a 60% chance that the output is correct, has no factual errors, then 60% of the time out of those outcomes, they are actually true. And this isn't just an empirical result that looks good on this plot, it's a theoretical guarantee of the method. And the last thing I want to show you, the second plot, shows you that we are doing what we promised. That is, if you look at the green bars, which correspond to combining both the end-to-end differentiation, that is learning an ensemble of scoring functions, as well as this idea of level adaptivity, that is adjusting the guarantee to the hardness of the problem, you'll notice that our bar consistently achieves our target of having at least 70% of the claims retained. Okay? So in other words, you can imagine a future in which you see these ChatGPT outputs slightly filtered to you, but attached attached to a probability that should carry some actual epistemic meaning, that you can say that 70% of the time I saw 70% from ChatGPT, that actually meant that was true. Okay. And so my last slide is just to say that this paper is an archive. You can read more about the technical details there. The actual underlying technology here is this idea from conformal inference that I've been working on called conformal inference with conditional guarantees. What we're actually doing under the hood is solving a ton of linear programs. So it's an incredibly compute-intensive problem, but we've done a lot of work to speed it up. And I can talk about that more, but I figured since I'm actually running just on time, I should really celebrate the fact that I kept this to 10 minutes as promised, and that you can check this all out yourself, but you can also ask me more questions.